Thank you for the invitation to speak here today. I'm going to be speaking today about finite element methods for geometric evolution equations. So by geometric evolution equations, what I mean are partial differential equations which govern the evolution of Riemannian metrics. And the specific model problem I have in mind here is normalized Ricci flow in 2 dimensions. So in order to describe the numerical methods that I'll be constructing, I need to first spend a little bit of time talking about numerical discretizations of scalar curvature. And once I've described numerical discretizations of scalar curvature, then I'll use those discretizations to construct discretizations of normalized Ricci flow in 2 dimensions. So actually, probably the first half or 2/3 of this talk will be devoted just to finite element methods for discretizing curvature. And the methods I'm going to describe are actually closely related to a well-known approximation of Gaussian curvature called the angle defect. So one of the most widely used approximations of scalar curvature on a triangulated surface is this so-called angle defect. It's what you get when you look at a vertex I in your triangulation, and you measure 2 pi minus the sum of the angles incident at that vertex I. So geometrically, it's what you get when you take this patch of triangles, you flatten it to a common plane, and you look at the angular gap which is formed. My notation that I'll use throughout this talk, I'll use the letter capital K to index triangles, the letter lowercase I to index vertices, and theta ik is the angle which is indicated in this figure here. So this approximation of Gaussian curvature is used widely in discrete differential geometry, computer graphics, discrete theories of relativity. And what I want to do today is talk about how to realize the angle defect in terms of finite elements and how to generalize it to higher order. So as motivation, I'll start by pointing out that the angle defect, well, it's manifestly a low-order approximation of Gaussian curvature. So one way to think about what's happening is if you have a smooth surface, what you're doing is by triangulating a surface, you're approximating a smooth Riemannian metric with a piecewise constant Riemannian metric. So a very natural question you can ask is, well, what would happen if I approximate G instead of with piecewise constants? Imagine I approximate G with piecewise polynomials. How would you define the discrete curvature in that setting? And what can I say about the convergence of such a discretization as I refine the triangulation? So if I let H equal to the maximum diameter of an element of the triangulation, if I let H go to 0, I would hope that my discrete curvature is converging to the true curvature of the underlying smooth surface as H goes to 0. And I would like to do this without using any embeddings. Right? Just like the angle defect is an intrinsic measure of curvature, you only need angles to compute the angle defect. I would like to construct higher order generalizations that also avoid using any embeddings. As a little bit more motivation, I'm going to give a little bit of a preview of some of the results in this picture here. So I haven't yet described the method I'm using to approximate scalar curvature with finite elements, but what I'm doing is I'm plotting the results of that method here to give some motivation. So what I've done here is I've taken a square equipped with this smooth Riemannian metric G. So the components of G are just polynomials here. I've triangulated the square with this triangulation, and then I've interpolated G with piecewise polynomials. So first I did piecewise constants, then piecewise linears, and piecewise quadratics. And then using the method that I'll describe in a few seconds, I've computed the discrete curvature of these piecewise polynomial approximants of G. You notice that in the lowest order setting, if I use piecewise constants, I get a very rough surface. If I use piecewise linears for GH, I also get a rough surface. If I use piecewise quadratics, I get something smooth. I should have said the z-axis here is the computed discrete curvature. So it's the kappa that's computed. So you see that even just from a visual standpoint, when you use low-order polynomials to approximate the metric, you get kind of not so visually pleasing results when you compute curvature. From an approximation theory perspective, this actually sort of makes sense. If you're computing a discrete curvature, you're in essence computing 2 derivatives of a piecewise polynomial approximation of G. if you want that to converge in, say, the L2 norm, you would hope that you're using polynomials of a degree at least 2 or higher. So that's manifested in this picture here. So that's some motivation. Now I want to describe in more detail how I constructed those figures. To do that, I need to be a little bit more specific about what I mean when I say I interpolated the smooth Riemannian metric G with piecewise polynomials. Really what I did was I interpolated G with what are called Regge finite elements. So these are some relatively new finite elements developed originally by Snorri Christensen, but in more detail by Larry Lee in his thesis with Doug Arnold. And what are these Regge finite elements? They are piecewise polynomial tensors on a triangulation, which have continuous tangential components across each edge. So here's the setup. I have a triangulation TH. I'll assume that this triangulation is just a triangulation of a polygonal domain in R2. You can generalize this, but for the talk, I'll just work on a polygonal domain in R2. I'll use EH0 to denote the set of interior edges of this triangulation. S is the set of symmetric 2x2 tensors. And the Regge finite elements are defined in this way. They are maps from omega to S, symmetric tensors, with the property that the restriction of sigma to any element is a polynomial of degree R, or each of the components is a polynomial of degree R. And the jump in the tangential component of sigma is 0 across every edge. Intuitively, what does this mean? It means that I have a piecewise polynomial metric with the property that if I have two triangles that are neighboring, then the length of the edge between them, as measured by the metric on the left, agrees with the length of that edge as measured by the metric on the right. So that's what this tangential continuity condition is saying. And lastly, I'll use the notation sigma h plus to denote the set of positive definite Regge finite elements, so the elements of this space that are pointwise positive definite. Okay, so that's the definition of the Regge finite elements. These are the piecewise polynomial tensors that I'm using to approximate G. And now what do I want to do? I want to, if I'm given one of these Regge finite elements GH, I want to define a suitable notion of a discrete Gaussian curvature of GH, which I denote by kappa H. Clearly, I cannot do that by just computing two derivatives of G. So the true Gaussian curvature is defined by an expression of this form, which involves second derivatives of the metric tensor G. Clearly, I cannot apply this to GH because GH has very low regularity. So instead of appealing to a formula like this, what I'm going to do is something very different. I'm going to take this expression for kappa, I'm going to linearize it around a fixed metric G. I'll discretize the linearization, and then I'll integrate the result. And they claim that if I do this, then I can get a nice notion of a discrete Gaussian curvature for GH. So that's how it's going to work. What do I mean when I say linearize the curvature? So I'm going to compute the linearization of kappa around a fixed metric G. So my notation here is I'm going to use mu to denote the volume form with respect to G. There's an explicit formula for the linearization of the scalar curvature multiplied by the volume form. It's given by this formula right here. If I linearize kappa mu about G in the direction of a perturbation sigma, so sigma is a perturbation of G, then the result is an expression of this form. So it's a second order differential operator, div s applied to that perturbation sigma, multiplied by the volume form mu. So here, div, this is the covariant divergence operator applied twice. So the result of applying two covariant divergences to a tensor, you get a scalar. And this quantity SG sigma is just a sigma minus G times the trace of sigma. This formula is valid only in dimension 2. In dimension 3, it's different. So another way of writing this expression here is, well, I can multiply by an arbitrary test function v and integrate over the domain. So if I rewrite this equation up here in that form, then what I have here is an expression for the linearization of the inner product of kappa with that test function v. So I differentiate the inner product of kappa with v, then I end up with this bilinear form here. is a bilinear form in the perturbation sigma and the test function v. So what I'm going to do in the next slide is I will integrate this result starting from the Euclidean metric, and I'll get an expression for the curvature. So we have an expression for the curvature kappa paired with an arbitrary test function v. It's equal to the integral of this bilinear form here. So it's a bilinear form parametrized by a metric tensor evaluated at g minus the Euclidean metric and the scalar test function v. So this bilinear form here is just div s sigma paired with v. So what's happening in this slide here is I know the curvature of the Euclidean metric is 0. I know what the linearization of the curvature is at any metric, so I can deform the Euclidean metric to my metric g, and along the way I'll integrate the linearization of the curvature to get the curvature of g. So why do I like this formula right here? I like this formula because I have an integral of a bilinear form parameterized by a metric. If I now insert discrete metric gh here and a discrete test function v into this formula here, now I have a discrete notion of Gaussian curvature. So that's what I'm doing here in this slide. I'm going to define a discrete Gaussian curvature by just performing a Gawlikian projection of that last equation. So again, I'm using Regge finite elements of degree r to approximate the metric. I'm going to use Lagrange finite elements of degree q to approximate the curvature. So Lagrange finite elements, these are piecewise polynomials of degree q that are continuous. So I define the discrete Gaussian curvature of one of these Regge metrics, gh, to be the unique function kappa h belonging to my Lagrange finite element space, with the property that if I take the inner product of kappa h with any test function vh in capital VH, it's equal to this integral right here. Mathematically, what is this equation saying? If I write everything down in terms of a basis for VH, what I have here is I have a mass matrix times the nodal values of kappa h is equal to some vector on the right-hand side. The entries of this vector are integrals of, are these integrals evaluated at each of the basis functions for capital VH. And what is this bilinear form here? I'm not using the original bilinear form because that's only valid for, you can only apply it to smooth metrics. I'm using the original bilinear form integrated by parts twice. So remember, my original bilinear form was this bilinear form. I've integrated by parts twice and I get this expression right here. So it's a summation over triangles of an inner product of SG sigma with the Hessian of that test function V. And then I have a summation over edges of the tangential component of sigma paired with a jump in the normal derivative of V. So if you're familiar with finite elements, you might actually recognize this bilinear form. It's actually a non-Euclidean generalization of another bilinear form that appears in a classic finite element method for the biharmonic equation. So this is this classic finite element method for the biharmonic equation called the Helen-Herman-Johnson finite element method. And they use this bilinear form when G is equal to the Euclidean metric. So this is a non-Euclidean generalization of that bilinear form. It's actually very familiar to finite element practitioners. Okay, so I've defined my discrete Gaussian curvature. I want to now convince you why this is a good definition of discrete Gaussian curvature for piecewise polynomial metrics. And for me, one of the most compelling reasons to believe that this is a good definition of discrete Gaussian curvature of piecewise polynomial metrics is that it actually reduces to the angle defect in the lowest order setting. So when you use the lowest order Regge finite elements, the degree r is equal to 0, the lowest order Lagrange finite elements, degree q is equal to 1, then this notion of discrete Gaussian curvature coincides with the angle defect. So more precisely, what this equation is saying is, here I have these basis functions phi, which are a basis for my Lagrange finite elements space VH. So these are the usual piecewise linear functions that are 1 at a single vertex and 0 at all of the other vertices. If I evaluate the inner product between my kappa h and one of these basis functions phi associated with vertex I I get precisely the angle defect at that vertex I. So it recovers the angle defect in the lowest order setting. And the proof is based on a certain identity where you compare the linearization of the angle defect with this bilinear form that we've talked about earlier. And actually this identity right here was first proved by Christensen for the case where GH is equal to the Euclidean metric. So it turns out that it generalizes to arbitrary metrics GH. And that's the key that allows you to prove this result. So this notion of discrete Gaussian curvature coincides with the angle defect when you're using the lowest order elements. But it's a generalization. It allows you to use higher order approximations of the metric to generate higher order approximations of the curvature. And you can actually analyze the convergence of kappa H to kappa. And really it reduces to kind of some standard finite element techniques, because when you're comparing kappa H with kappa, the discrete Gaussian curvature with the smooth Gaussian curvature, you can do that by just comparing two bilinear forms. One is evaluated on the discrete objects, and one is evaluated on the continuous objects. So you perform some estimates, and you can actually prove some error estimates for how close the discrete Gaussian curvature is to the exact Gaussian curvature of the underlying smooth metric. So I won't go through the details of this slide, but I'll just kind of describe roughly what it's saying. If you take a smooth metric G, and you approximate it with a sequence of regular finite elements GH, which is approaching G, then you can prove that the difference between kappa H and kappa is getting smaller and smaller and smaller as you refine your triangulation, provided that GH approaches G. It's maybe easier to look at this estimate at the bottom of the slide. At the bottom of the slide, I've written down this estimate for the case where I'm using the L2 norm to measure the error. It says that the L2 norm and the error between the discrete Gaussian curvature and the exact Gaussian curvature is bounded by a constant times certain powers of H. And you notice that these powers of H, well, in order to get convergence in the L2 norm, I need R to be at least 2 to get convergence, which is what we mentioned earlier. So now we can go back to this figure and understand a little bit better what was happening. In the cases when R is equal to 0 or R is equal to 1, piecewise constants or piecewise linears, when you compute the discrete Gaussian curvature, you get something which doesn't converge in L2. And it's manifested in the pictures. When you use higher order elements, degree 2 or higher, you get a nice picture, and that converges in L2. So here are just some numerical examples. When you use degree 2 or greater, you get convergence in the L2 norm. Here, when R equals 2, you get first order convergence. No convergence when you use degree 0 or degree 1 finite elements. Okay, so how much time? Just a couple of minutes. So I'll just kind of briefly explain how this can be applied to geometric evolution equations. So we did a lot of the hard work already, so now the rest is more straightforward. So imagine that I take a geometric evolution equation like this. The time derivative of a Riemannian metric G is equal to some given function sigma, and I'll assume sigma is a function of G and the scalar curvature kappa. So what I'm going to do to discretize this, first I'll rewrite this as a system of differential equations. One will be the differential equation for G, and one will be the differential equation for kappa. Actually, I'm going to use the differential equation for the densitized curvature, kappa times the volume form. We know what the differential equation for kappa is. The right-hand side is that same div-div operator we saw earlier. If I discretize this, well, I discretize the first equation, and I discretize the second equation using the same sort of technique that I used before. The derivative of the inner product of kappa H with any test function VH is precisely that bilinear form that we've seen several times throughout this talk. You can apply this to Ricci flow. So here I'll consider Ricci flow in 2 dimensions. In 2 dimensions, it looks like this. The time derivative of G is 2 times the average of the scalar curvature minus the scalar curvature times G. If I discretize it using the method I just described in the last slide, I get this system right here, which is equivalent to a system of ODEs that you can solve with the time integrator. And you can say some nice things about the structure preserving properties of this discretization. You have a discrete Gauss-Bonnet theorem, exact preservation of area, and you recover the angle defect in the lowest order setting. if I had more time, I would show. Well, actually, I had a movie which I was going to show, but the movie is, as I understand, is not working on this PDF. But what you would see here is this this surface. When I run my discretization of Ricci flow on it, it would be deformed into a sphere as t goes to infinity. Okay, so those are some conclusions, and I'll stop there and just say thank you for your attention.